In this video, we're going to be talking specifically about stereochemistry of alkenes, meaning compounds with double bonds in them. So we've already seen some kind of stereochemistry with alkenes. We saw the cis-trans notation in cyclohexane derivatives, and cis meaning the same side and trans meaning the opposite side. This is what we call relative stereochemistry. Relative meaning it only applies when there's one or two things you're comparing to be cis or trans. We need to kind of know what the molecule looks like to be able to determine whether something is cis or trans. It is not an end-all be-all for stereochemistry, and in fact, when you have more than one, as we saw with cyclohexane derivatives, if you have three substituents on the cyclohexane ring, you can't use cis or trans, and we'll see that if you have more than one alkene in the system, you can't use cis or trans. So we have to have something what's known as absolute stereochemistry to be able to talk about situations where you have more than one option for cis or trans. And in alkenes, the absolute stereochemistry is called EZ notation. Comes from the German word for opposite, and Z comes from the German word for same. So similar to cis or trans, we're talking about things that are on the opposite or same side of a double bond, but this will be the absolute stereochemical notation. So we can use this for systems with multiple or many different double bonds in the system. So when we are talking about E and Z notation, we have to have some way of assigning this notation to a given alkene. And this is given by a set of rules called the Kahn-Ingold-Prelog rules. And these assign a priority to a double bond. Meaning what is the highest priority, what is middling priority, and what is the lowest priority. So let's consider a system that looks something like this, and let's go about assigning E or Z notation and assigning priorities. So let's say we have a methyl group here, we have an H here, we have an F here, and we have a Br here. So the first rule in assigning priority is higher priority comes from a larger atomic number. So the higher the atomic number, the higher priority. So what we're going to do is we're going to take this double bond, we're going to split it down the middle, and we're going to compare the substituents on either side of the double bond and see which one is high and which one is low. So between an H and a carbon, the carbon is going to be the higher atomic number, so our higher priority substituent would be this CH3. If we look at fluorine and bromine, bromine is going to be the higher atomic number, so bromine will have the higher priority on this side. Finally, to determine whether it's E or Z, we look at the relative position of these high priority groups to one another. In this case, they are on the same side of this double bond, so we would say that this is going to be a Z alkene because they are on the same side of the double bond. If they were on opposite sides of the double bond, we would say that it is an E alkene. So let's look at some more examples about determining priority and determining E or Z notation for double bonds. So let's look at another example. So let's look at, for instance, this example. So I have an F, I have an H, I have a CH3, and then I have a CH3, CH2. And the question is this an E or Z alkene? So first what we're going to do is we're going to divide it down the center. And then we're going to look at both sides and determine which one is low priority and which one is high priority. Between an H and an F, F has a higher atomic number, so our F will be our high priority group on this side. Now, in this case, it is a little less simple because we have a carbon and a carbon. So when we have two atoms that are the same, we have to go one atom out from whatever we're comparing. So we could say the first layer is carbon on both of these, and then the second layer, as it is out, we have two H's and a carbon that it's connected to. So our second degree out would be HHC. In this case, our second degree out from this one would be three H's. So we have H, H, H. And then we compare again, and we see that we have H, HC, H, H, H. The H's are the same. But in this ethyl group up here, we have a carbon versus a hydrogen. Since carbon is going to be a higher atomic number than hydrogen, our higher priority group is going to be this ethyl group here. Finally, to determine the stereochemistry of this alkene, we look at the relative position of these higher priority groups to one another. We see that they're on the same side, so this would be a Z alkene. Let's look at a couple more examples. So let's look at this one. So we have a bromine and a hydrogen, and then we have a carbon and an OH, and then we have a double bonded H. So again, starts the same way. We're going to compare on either side of the double bond. We have an H and a Br. Br has the higher atomic number, so Br will be our higher priority on this side. On this side, we go one out. We see we have a carbon and a carbon. So the first one is going to be carbon. The first one is going to be carbon. So we can't compare there, so we have to go one further out. Remember that there is an H here. So we have an O, an H, and another C. So our second degree out is going to be OHC. And our second degree out here is a little more complicated. We see we have this double bond. Whenever we have a double or a triple bond, double bonds will count two. We'll count two priority assignments for that particular atom. Triple bonds, we will count three priority assignments. So in this case, we have one bond to an H and two bonds to O. So if we're comparing out, we have our carbons. That's where we can't stop. We have a hydrogen, we have an oxygen, and then we have an oxygen and a carbon. Since we have an oxygen which is higher in atomic number than our carbon, this will be our higher priority substituent, so this is going to be our higher priority substituent here. We then look at the relative position of the high priority groups to one another. We see they are on opposite sides of the double bond. So in this case, this alkene would be assigned E. It would be an E alkene. Finally, let's do one example that combines all of these rules together. So let's see. So I have a C double bond O, and then I have a triple bond, and then I have a CH2F and a CH2Br. Okay, so we're going to start the same way. I'm going to start on this side. We have a carbon and a carbon. So our first one is carbon, so we can't stop there. Our next one is going to be two hydrogens and an F, so HHF. This one is going to be HHBr, HHBr. Our H's get crossed out because they're the same. Then we say we're comparing F and Br. In this case, Br is higher priority because it has a higher atomic number, so this CH2Br is going to be higher priority. Now we'll compare the other side. We go one out. We have a carbon and a carbon. So our first layer is carbon, so we can't stop there. We then see we have two bonds to H and another bond to a carbon. Remember, this is a CH3 group. So we have OOC. In this case, we have three bonds to carbon, so those will be all of our bonds. We have CCC. Our C's cancel out, and then we're comparing OO with OC. O is a higher atomic number than C, so in this case, this group here, this acetyl group, would be the higher priority group. We then finally compare the relative location of the two high priority groups. We see they're on opposite sides, so we would call this an E alkene.